It is the summer of 1944, somewhere in the bocage country of Normandy, France. The hedgerows press in on all sides, dense ancient walls of earth and root that have stood for centuries, now turned into a killing ground neither side had fully anticipated. A German Panzer IV sits at the edge of a lane, its engine idling, its crew confident behind nearly 40 millimeters of rolled steel armor. They have survived artillery, small arms, even the occasional rocket. They know what it takes to destroy a tank, and they know the frightened British infantrymen moving through the shadows of those hedgerows do not have it. Or so they believe. What happens next takes less than 3 seconds. There is a sound, not a tremendous explosion, not the roar of a heavy gun, but something closer to the sharpened crack of a door being slammed shut by a violent wind. A shaped jet of superheated copper, traveling at roughly 8,000 meters per second, punches clean through the armor as though it were tinfoil. Inside the tank, the effect is catastrophic. The pressure wave alone is enough to kill. The spalling metal that follows is worse. And then, if the fuel or ammunition catches, the crew, should any have survived that initial instant, have no time at all. The Panzer IV, impenetrable to almost everything else the British soldier carried, has been destroyed from the inside out by a grenade that fits in the palm of a man's hand. The weapon is the number 68 anti-tank grenade, and later its more famous descendant, the number 74 sticky bomb, and the broader family of shape-charge handheld munitions the British infantry carried into the most brutal tank country in Western Europe. But this is really the story of a physics principle that terrified Germany's armoured core, a principle the British understood and weaponized at precisely the moment history demanded it, and a principle that, in the hands of ordinary soldiers, made some of the most formidable armor of the Second World War suddenly, horribly vulnerable. To understand why this mattered so profoundly, you have to go back to the autumn of 1939 and appreciate the sheer scale of the problem facing British military planners. Germany had invaded Poland with roughly 2,500 tanks. By May 1940, when the Wehrmacht crashed through the Ardennes and into France, the figure had grown and, more importantly, the tactics had evolved into something the Allies had no coherent answer to. The Blitzkrieg was not simply fast, it was psychologically shattering. Armour moved ahead of infantry, cut off supply lines, encircled divisions, and left entire armies confused, leaderless, and destroyed before they had properly understood what was happening to them. The British Expeditionary Force evacuated from Dunkirk in June 1940, leaving behind nearly 64,000 vehicles, including virtually every piece of heavy anti-tank equipment it possessed. The British Isles braced for invasion. Home Guard units were issued instructions, some now almost comically inadequate, though anything but comic at the time, on how to stop a tank with petrol bombs and improvised obstacles. The standard infantry anti-tank rifle, the Boys, could penetrate roughly 21 millimeters of armor at 300 meters. German armor was already exceeding that. The heavier anti-tank guns, the 2-pounder and eventually the 6-pounder, were effective but immobile, useless to the infantryman, caught alone in a field, a wood, a narrow French lane, with a tank bearing down on him, and nothing but his personal equipment between him and death. What was needed was something a single soldier could carry, something that could be thrown, fired, or pressed against armor and reliably destroy it at close range, something that did not depend on the mass or velocity of a conventional shell, but instead on a different principle entirely. A principle that, in 1888, an American engineer named Charles Monroe had accidentally stumbled upon, and which no one had yet fully exploited in the context of personal infantry weapons. The challenge was not conceptual, it was engineering, and it was time. The principle at the heart of what follows is known as the Monroe effect, or the shaped charge effect, and it is worth understanding clearly because everything else in this story depends upon it. A conventional explosive creates a pressure wave that expands in all directions simultaneously. The energy is dispersed. Some of it does damage, much of it is wasted. But if you line a hollow cavity within the explosive with a thin layer of metal, copper being particularly effective, and you shape that cavity into a precise cone, something remarkable happens when you detonate it. The explosion does not expand in all directions. Instead, the detonation wave collapses the copper liner inward upon itself, compressing and accelerating it along a single axis into what physicists call a hypervelocity jet. This jet, not a solid projectile, but a stream of superplastic metal moving at velocities approaching 8 kilometers per second, does not blow through armor the way a shell does. It cuts through it. It penetrates not by force of impact, but by a process of hydrodynamic penetration, in which the jet and the armor plate briefly behave almost like fluids, the jet boring a channel through steel the way a stream of water bores through soft earth. The implications were staggering. A conventional shell needed enormous velocity to penetrate armor, which meant a large, heavy gun, a heavy carriage, enormous amounts of propellant, and a static firing position. A shaped charge needed none of that. It needed only to reach the surface of the armor and detonate at precisely the correct standoff distance, the gap between the tip of the copper cone and the face of the steel, to produce the maximum length and coherence of jet. The standoff distance was crucial. Too close, and the jet had not fully formed. Too far, and it began to disperse. Get it right, and even a relatively small charge, small enough to fit in a hand grenade, could penetrate armor that would laugh off most conventional projectiles. Work on British shaped charge infantry weapons was being conducted at multiple establishments across the country by 1940 and 1941, most notably at the Projectile Development Establishment at Fort Holstead in Kent and at the Armament Research Department, which maintained close liaison with university physics departments whose understanding of detonation physics was essential. The scientists and engineers involved were not, in many cases, traditional military men. They were chemists, physicists, and mechanical engineers pulled into war work, given problems that had no handbook solution, and told to find answers quickly. The number 68 grenade, a rifle-launched anti-tank projectile, had actually entered limited service before the shaped charge principle was fully refined, relying on a more conventional impact mechanism. It was the number 74 sticky bomb and the broader development effort running in parallel that began to harness the Monroe effect in earnest. The number 74 grenade, officially the anti-tank grenade, number 74 Mark I, though no soldier in the field ever called it that, was designed by Stuart McCrae and Cecil Vanderpeer Clark, two of the most creatively unorthodox weapons designers the British military had ever reluctantly employed. Clark, in particular, was a man whose relationship with institutional caution bordered on open contempt. He had been working with McCrae and the staff of what would become MD1, Military Department 1, the so-called Churchill's Toy Shop, housed at the Firs in Whitchurch, Buckinghamshire, developing unconventional weapons outside the normal procurement channels, with Churchill's personal backing and the perpetual irritation of more conventional military departments. The sticky bomb they created was, in essence, a glass sphere roughly the size of a large grapefruit, approximately 115 millimeters in diameter, filled with approximately 567 grams of nitroglycerin paste, and covered in a layer of strong adhesive. It was encased in a sheet metal shell for carrying, which was removed before use. When the lever handle was pressed and the bomb thrown or pressed against armor, the adhesive sphere stuck. and then detonated. The shaped charge element of the number 74 was relatively crude compared to what would follow, but it did not need to be sophisticated. The nitroglycerin charge, placed directly against the steel at the moment of detonation, was enough to punch through the side armor of most German tanks of the period, typically between 30 and 50 millimeters on the hull sides. The detonator was a 5-second fuse, long enough, just, for the soldier who had pressed it against the tank to run. In theory. In practice, the weapon demanded extraordinary courage, and the risk of self-injury was acknowledged even in the official documentation. The Home Guard, which received it in large numbers, roughly 2.5 million were manufactured before production ended, regarded it with a mixture of gratitude and terror. It was better than nothing. That was not a high bar, but in the summer of 1940, it was the bar that mattered. If you are finding this interesting, a quick subscribe helps more than you know. The more technically sophisticated developments came as the war progressed, and British industry had time to refine what the shaped charge principle could really achieve. The PIAT, the Projector Infantry Anti-Tank, entered service in 1942 and represented a fundamentally different delivery mechanism for essentially the same physics. Rather than a grenade pressed against armor or lobbed from a rifle, the PIAT launched a 1.1 kilogram shaped charge bomb using a powerful spring and spigot system, achieving an effective range of roughly 100 meters against stationary targets, somewhat less against moving ones. It weighed nearly 15 kilograms, heavy, uncomfortable, and with a recoil that could dislocate a shoulder if the firer was not braced properly. The cocking mechanism required compressing a spring of nearly 90 kilograms of force, which in practice meant lying on your back with your feet in the stock and hauling upward with both hands. The shaped charge warhead could penetrate up to 102 millimeters of armor at right angles, enough to threaten the side and rear armor of a Tiger I and to reliably destroy most other German armored vehicles in service. The Germans, for their part, were not unaware of the principle. The Wehrmacht had been issuing the Haftholladung, a magnetic hollow charge device, from 1942 onwards, and the Panzerfaust, the most widely produced anti-tank weapon of the entire war, used a shaped charge warhead fired from a disposable launcher. Roughly 8.25 million Panzerfausts were produced between 1943 and 1945. A staggering figure that reflected both the simplicity of the design and the desperation of the German military position by the final years of the war. The Panzerfaust 30 could penetrate approximately 140 millimeters of armor at 30 meters. Later variants extended both range and penetration. It was, in many respects, technically superior to the PIAT in terms of penetration figures, and it was vastly cheaper and quicker to produce. What the British had that the Germans did not, however, was time and circumstance on the side of the defender. The PIAT was primarily a weapon of ambush and close-quarters defensive fighting, of hedgerows and rubble, of city blocks and ruined farmhouses, of the precise kind of terrain that nullified the range advantage of conventional anti-tank guns and brought armor into the killing range of the man with the spring-loaded launcher and the shaped charge warhead. In that environment, the technical differences in penetration figures mattered less than the tactical reality of the engagement. A PIAT team in a ruined building in Caen could engage a Panzer IV at 10 meters. At 10 meters, almost everything about the comparative specifications becomes irrelevant. The American answer, it should be noted, was the M9A1 bazooka, a rocket-propelled shaped charge launcher that offered somewhat greater range than the PIAT and was considerably lighter at approximately 6 kilograms, though the rocket signature gave away the firer's position, and the shaped charge penetration of approximately 100 millimeters was roughly comparable. The bazooka entered service in 1942 and was widely supplied under Lend-Lease to Allied forces. The two weapons complemented each other in different tactical roles, though British and Commonwealth forces predominantly relied on the PIAT throughout the North-West European campaign. The legacy of what these weapons achieved is genuinely difficult to assess, with the precision that history sometimes pretends to offer. Confirmed tank kills attributable specifically to shaped-charge infantry weapons are hard to separate from the overall casualty figures of armored warfare, in which artillery, air attack, mechanical breakdown, and anti-tank gunfire all played their parts. What the records do show, and here the regimental war diaries, the German after-action reports, and the testimony of surviving crewmen on both sides largely agree, is that the psychological effect on tank crews of knowing that any infantryman in any hedgerow might be carrying something capable of killing them was profound and enduring. German tank commanders in Normandy repeatedly noted the effectiveness of British close-quarters anti-tank tactics, and the casualty rate among panzer crews in urban and bocage fighting was substantially higher than in the more open country of the Eastern Front, where range and mobility could be exploited. Entire German tactical doctrines around tank-infantry cooperation were influenced by the need to prevent enemy infantry from closing to PIAT range. The weapon that fit in a British soldier's hands had changed how German armour was compelled to behave. 9 Victoria Crosses were awarded to PIAT operators during the war. The most celebrated is perhaps that of Major Robert Henry Kane of the South Staffordshire Regiment, who during the Battle of Arnhem in September 1944 used a PIAT and later a 2-inch mortar to single-handedly destroy or damage at least 6 tanks and a number of self-propelled guns over 9 days of almost continuous fighting, while wounded on multiple occasions and frequently operating in conditions of extreme physical exhaustion. His citation describes him as having displayed outstanding devotion to duty. It is a phrase that does scant justice to what the man actually did. He was the only recipient of the Victoria Cross at Arnhem who survived to receive it. His PIAT, a weapon that had been designed in a converted country house by engineers whose names barely register in most histories of the war, had held the line. Original PIAT launchers and number 74 sticky bombs can be seen today at the Imperial War Museum in London, the Tank Museum at Bovington in Dorset, and at various regimental museums across the United Kingdom. They are unimpressive objects to look at. The PIAT in particular, dull metal, heavy, awkward, suggests nothing of what it was capable of. That is perhaps appropriate. The men who carried it were not remarkable to look at either. Return, then, to that Normandy lane in the summer of 1944. The Panzer IV sits in the dapple shadow of the bocage, its crew still confident, still certain that the men moving in the hedgerows cannot touch them. They are wrong, and they do not know it yet. In the hands of a lance corporal from Birmingham or a private soldier from Glasgow, there is a device that weighs 15 kilograms and looks like something that might have been assembled in a factory workshop on a Tuesday afternoon. Which, in a sense, it was. It contains no magic. It contains physics. It contains the Monroe effect, the shaped copper jet, the hypervelocity penetrator, the understanding that armor is only armor until the right principle is applied against it. The Germans built the finest tanks in the world in the Second World War. They built armor that by conventional measures should have been immune to anything a single infantryman could carry. They were right about the conventional measures. They had not fully accounted for what happened when British engineers stopped asking how to build a bigger gun and started asking a different question entirely. Not how do we hit harder, but how do we make the armor destroy itself? That question, asked in a requisition country house in Buckinghamshire, answered on factory floors across the Midlands, and tested in the most brutal conditions imaginable in the hedgerows of France, changed the arithmetic of armoured warfare permanently. The tank was never invulnerable again, and the man on foot, with the right knowledge and the willingness to close the distance, was never entirely powerless. That is what a handful of physicists, a few unconventional engineers, and several million workers in British factories gave to the infantrymen of 1944. Not certainty of survival, just a fighting chance. That, in the end, was enough.